Okay, if you want to ask a question, yeah, go ahead and ask a question, Leslie. Yeah, we'll do the recap in maybe in about 30 minutes time. So we've got one particular question right now in the Ask Me Anything, which is what is pre-training in deep neural networks? So that is a simple question, quite interesting to answer. So let's go directly to that part. So we're going to go to the part where we're talking about transfer learning. Okay, so I'm going to blow up the slide here. Okay, so so don't worry if you don't understand yet. I know we have a lot of people here to hear the lecture and to start from the beginning, and that's fine. But as Leslie said, it's also not very fair to people who've come just to ask a question or two. So those of you who get whatever you need out of the help session, feel free to drop off and enjoy the rest of your day. Okay, so in transfer learning, what we are doing is basically trying to use a neural net that has been trained on a previous task. Okay, so for example, for convolutional neural networks, we might have trained on ImageNet, which is an image classification problem. You know, you're faced with images of objects, and then you're trying to classify what they are. Okay, now you understand that when we start off learning the parameters of a algorithm, especially in this gradient descent method, we have to start from a set of weights already, okay? So we start with a set of weights. Usually we might say it's all zeros, okay, in the case of a linear algorithm, okay? And then we are going to use the gradient to decide which way to move our weights around, okay? Now in the neural network, because we have multiple neurons inheriting the same set of weights at this level upstairs, right, at level L compared to the inputs at L minus one, it's important not to start all of those weights at zero. They're usually randomly perturbed, okay? But what we find is that because of the way a lot of layered algorithms work, the stacked ensembles work, okay, is that they build primitive features, these nonlinear functions, okay, nonlinear mappings. They build from these primitive inputs more complicated and more interesting features that go up. Okay, so if you can remember from a the image recognition problem, right? We might have an input which is a raster image of all of the pixels. Okay, so I have something like this, a big raster image of things, right? And basically, I would have something like M by M, right, to get M features in total. Okay, so when I do that, I have all of these gigantic amount of features, and then I need to engineer higher level features, right? One way we do that is by looking for symmetry or, you know, darkness or other things of this sort. So we can think about all of these things that we could use to build these. Now, when we successively array or stack layers, the intermediate layers basically build these, you know, basic features. So we can see in a convolutional neural network, one that's attuned to vision or spatial blocks, right? What we see are textures like straight lines, circles, or textures being composed in the intermediate steps. And at the higher level steps, you might see actual objects, right? So if we have a very large receptive field, we might see things like eyes or noses or hair textures. And then these themselves will be arrayed at even higher levels to recognize faces. Okay, so when we talk about transfer learning, actually what we mean here is that instead of starting with an entirely uninitialized network, we might start with a learned network that is already adapted for some task, okay? So for example, in this case here, let's see whether we can do the slides, okay? All right, so here we might have an original network, okay, that's here, okay? So this is the bottom, this is the input in gray. And then through the image network, we're building successive more and more features Okay, so these might be, straight lines, some textures, etc. Okay, building up to things like eyes and faces. Okay, because each of these layers are basically combining features from the bottom layers. Okay, and then finally at the top, if you remember what happens in something like VGG, we have our output layer, which is in this pink, right? Which is supposed to classify an image to one of several categories. Okay, so ImageNet might classify to about 1,000 classes uh, of objects. Okay, and let's say you're doing another type of image recognition task, but it's not the same objects. Okay, so when we don't have a lot of data, what we might want to do is decide to do this idea of pre-training. Okay, so pre-training means we take this entire network that we've just circled in this oval, we use the whole thing, but we take off the top parts. Okay, so as it's indicated with this red X, right, we remove this, we throw it away, and we attach a new head, a new top layer to the network, okay, that's not trained yet, okay, just randomly initialized. And so the idea with pre-training is like all of your weights down here, all of the, all of this theta that you have is already pretty good at taking raw images and creating features, okay, learning useful features. Okay, so those useful features are things like what we said here: eyes, faces, wheels, I don't know, metal panels, glass, etc. Anything that we could compose out of basic features, okay? And then what we're training is this top layer, okay? This is a new top layer that's going to use those learned useful features from the pre-training, okay? And then use those in some way to create a classifier, create a new classifier. Okay. The whole point is like when we're doing pre-training, we're saying that the bottom part of the stack, which is our learned features, are somehow pretty good. They could be useful for more than one thing, okay? Again, if we're doing it on ImageNet, which are real photographs, then we expect a lot of other things that we would find, different types of dogs, for example, or things of this sort, natural scenery, to also have, to take benefit from what we can discern from these learned features. Okay, so let's see whether that answers your question. Okay, so that is what we mean by pre-training in deep neural networks. Okay, so the idea is, again, we take maybe a very large data set, okay, and we do something interesting with it, okay, to try to actually optimize a task. So for example, if you take the natural language processing course next semester or even this semester, because Prof. Hung is teaching it as well, you'll learn something called embeddings, okay? Embeddings. And actually, you guys have a bonus notebook. You have a 09 bonus notebook for this if you care to do it, but you don't have to, it's not tested. Okay, and embeddings basically use a very, very large corpus of text to try to get some idea of how words relate to each other, okay, which words appear in context to each other. And they use this type of pre-training language model to be able to learn other things. For example, how do different words display sentiment? Okay, so you can understand it. If I know that certain words correlate together a lot, then I might have a better idea of how those words might impact whether there's a positive or a negative sentiment for a particular sentence or tweet, for example. Okay, so pre-training is that sort of thing. Basically, taking another task, okay, as it says here, taking another task, okay, which is the beginning network here, okay, using it to start or initialize the weights, okay, of a neural network. Okay, so we're just going to say that this network over here, okay, instead of starting with random values for its network, it's going to start with the pre-trained values, at least for the bottom layers in golden, yellow, and blue, okay? And then the top layers over here are then subject to random initialization, just like we would do from a plain neural network that we're training from the very beginning, okay? So that's what it says here. If you have a lot of data, then you might as well just start with a plain network, okay? We could use something like a pre-trained network as an initialization point, which is what a lot of people do, right? And then retrain it from the bottom up. That means we allow all of the parameters here, all of them, to change, okay? But when we don't have enough data, if we let the bottom parts change, that may not be a good thing. That means our primitive features that we're looking for either in words or in video or in images are changing, okay? Maybe we don't think straight lines are mean a lot, okay? But in reality, we think, you know, image features are conserved over many different tasks, very basic ones like edges and corners and textures, okay? So that's why it really depends on how much data you have. If you have enough data, retrain the entire network. If you don't have enough data, go ahead and freeze part of the network. Okay, maybe we'll just say, for example, here, this part down here is going to be frozen. I'm not going to allow you to change anything here because I think those basic features are pretty good. Okay, uh, so if I think that's the case, then I'll just train up here. Okay, train this. All right. Okay. So there's another couple questions. Let's take them one at a time. So I saw Leslie has a different question in chat, but let's make sure we get to the other question first that came up on the, oops, yeah, on the Ask Me Anywhere. So just let me look at that for a second. Okay. That one asked about activations. Okay. So what is an activation function? Okay. So we'll take a look at this. Okay. So we need to go back a little bit to the deep neural network problem. Okay, where is the activation slide? We had it early on. Okay. I thought I had another slide with that information. Okay. Yeah. Okay. So an activation is a function that allows us to make a nonlinear change to the layers, okay? So let's just go to that part here. Okay. So I thought there was another slide here, but maybe not. Okay, the important part here is that when you have an activation, okay, all the ones that are on the right side of this part, okay, these are all functions that take a signal and then map it non-linearly to the output, right? So we have an X, okay, our input. So let me just draw this for you for a second. Okay, so I have a neuron here. It's got some inputs, okay, let's say 3 inputs, and then it's going to output a new signal, right? A new signal S, okay? And our signal S is going to be something like taking the coefficients and multiplying it by these inputs, X1, X0, X2, X3, okay? Something like that, okay? So we're just going to take the weights that are associated with these edges, right? So I have theta 1 here, theta 2, and theta 3. Okay, now when I multiply them all together and I do something like add them all, okay, which is a dot product, right? Then I could pass that as out, okay? But when I do this, actually, if I don't do any other types of nonlinearity, okay, actually when I stack one layer of perceptrons over another layer of perceptrons, and I just add these things together, I'm going to get another perceptron out. Okay, meaning that it's just going to be another hyperplane. Okay, that hyperplane I could have gotten just from a single layer. I didn't need 2 or 3 layers to get it. okay? So when I just use this as is, okay, meaning this particular thing, all right, without any other functions, I'm going to get out again another perceptron. So whether I have multiple layers or a single layer really doesn't matter, okay? In order to get more complicated behavior, okay, I need to be able to draw more interesting boundaries, okay? So for example, you saw in the one nearest neighbor case, nearest neighbor, okay, that it actually consists of a bunch of straight line segments, okay? It's not the same as a hyperplane because a hyperplane has the same hyperplane throughout the entire input space, okay? But KNN has many of these segments all stuck together, glued together by virtue of the data set. And it's similar, like this week, you'll see for decision trees, okay? So you can see the boundary of a decision tree is also this type of fragmented axis parallel thing, okay? So in order to get a good output that is not going to be just a simple hyperplane, we need to have a nonlinearity, okay? So the nonlinearity can be something like what we talked about here. Sorry, wrong symbol. Let me go back to the line. Okay, so both of these do the same thing. They take an input, a signal from possibly infinity, okay, to negative infinity, and they do something with it. They map it non-linearly to another output, right? So if I were to map it linearly, that would be very simple. It'd be something like this, right? A straight line going through. But in fact, it's a nonlinear transformation, right? So in both sigmoid and hyperbolic tangent, it's some type of S curve, okay, that has some bounds, right? So between positive 1 and negative 1 for hyperbolic tangent, and between 0 and 1 for sigmoid, okay? So this is the only way that through something like an activation function, which has to be, very importantly, non-linear, okay? You cannot draw a line for the entire segment, okay? For the entire domain, okay, from positive infinity to negative infinity, then we can get more complicated boundaries, okay? So that is the most important thing that we are saying about activation functions, okay? So I hope that answers your question. If not, let me know. There are different activation functions. We usually in neural networks prefer very, very simple things, okay? So you can see the hyperbolic tangent is fairly easy. The simpler one is a ReLU, right? You've seen the chart of a ReLU function, right? Basically, it looks a little bit like, yeah, I'll just draw it here again, okay? Something like this, okay? If I have, again, the signal that goes from negative infinity to positive infinity, okay? So this is the signal on the x-axis. Then the ReLU function just has an identity function, which is just x, meaning I have a slope of 1, right? And a 0 function here, right? There's a discontinuity at 0, but basically everywhere else it has a derivative, right? 0 on this side and 1 on this side. So that is really almost the most simple type of nonlinearity function that we could describe. Okay, and as it says in the lecture, there are a number of other ones that you can try that give you slightly different output. Okay, so hopefully that helps you figure out what is pre-training for DNN. That's an important part of making sure we understand that when we stack layers upon layers, if we don't have, sorry, I highlighted the wrong one. If we don't have an activation function, we're just going to get back simply another linear hyperplane, okay? Because when you add two lines together, you get another line, right? So the only way we can do that is try to put some nonlinear function through it, okay? All right, so I've answered the two questions on Ask Me Anything. Let me answer Leslie's other question on the CNN, okay? All right, so how does the CNN specifically learn more about a feature, okay? It doesn't specifically learn it. It does this based on the loss function. So it's just a stochastic property that when you have lots of neurons, they can start to specialize, right? So if you can think for instance, let's see whether we can find, oh, I'm looking at the wrong screen here. Okay, let's take a look at a neural network. Okay, so here we have the original features. Okay, so these are our features. They might be pixels, for example, coming from our raster image. Okay, and at each of these, at our first layer, okay, at this layer here, layer one, um, all of these neurons here, the three A's that I'm looking at, right? This one, and this one, they're all getting the same input. They're getting a bias term of one, an x of one, x2, and all the way to xd. Okay, so all of these things are being fed into each of these three neurons. Okay, now if they were initialized the same way, meaning that they have the same current weight, they would all move in the same direction. Okay, because the loss with respect to that value would be the same because well, all the inputs are the same. Okay, so they may be perturbed a little bit. They may start with different initial weights, which is very, very key for a neural network. Okay, and then some of these will start to be able to pick up through many rounds of training specialization because you know, downstream. Sorry, I'm using the wrong thing again. Okay. Um, I should say upstream. Upstream in the neural network, there will be reliance on different pieces of information, different abstractions that are coming together that will help it learn whether this particular object that we see as the pixel input is a dog or a cat. Okay, so you can think about what things you would use to identify a dog and a cat. Okay, so we might use fur, eyes, an open tongue or something like that, okay? So all of these pieces of information, somewhere in the network, if we have enough of these neurons per level, some one of these neurons will start to be able to find features that are dependent on earlier layers that will help build some nonlinear mapping representation that will be helpful for upper layers, okay? So that's how it goes, okay? So to answer your question, Leslie, in a nutshell, there is no particular way that we can guarantee that a part of the neural network is learning a particular feature, okay? It's just comes out of the fact that we have lots of neurons, okay? So we have many things, okay? And that they're initialized differently, and they see all of the input at the previous level, you know, in a different way, okay? Because ultimately we're trying to think about how the loss, right? The loss on this particular task, okay, could be engineered better, right? So when we pass down the gradient in this direction, each of these nodes at this level, okay, will receive the gradient and decide, okay, it's better to change my weights about the things in the yellow over in a different way, okay? So some of them will learn, you know, particular features that are maybe uh, textures. Some of them might learn edges. Some of them might learn corners, especially at the lower levels. And at the higher levels, it's basically trying to decide how to pull these together to get you know, more composite features. So you can think, for example, fur, right? Fur is a type of texture, right? There are different types of fur, and they have different primitives, right? So some of them might look a little coarse, some of them might look a little wiry because the, you know, the threads on the fur are very thin. Some might be very thick. Okay, some of them might be a certain color. Those types of primitive features would be found at the previous layer, right? At the layer that comes before, or even the ones before that. Okay, so basically a layer that's downstream, or sorry, closer to the end of the network, is basically trying to compose features that it gets at the previous layer to decide how to create something that would be useful for the eventual end task. Okay. Okay, so I'll go over that a little bit more because when we talk about the first part of deep learning, we'll get to that. Okay. Okay, we don't have any other questions on Ask Me Anything, so I'll just ask answer the last question that Leslie has. But then if you guys have any more questions, please ask. I mean, the whole point of a help session and a lecture recap is to assist you in learning in different ways, especially if you watch the lectures and you found them, okay, pretty confusing. This is why we do that. don't hold back. Okay, Leslie, if you have more questions, ask them. I will definitely do stop around an hour in if we haven't gotten to the lecture recap. So don't worry. Go ahead and ask your questions. Okay, so let's talk about the transfer learning again. Okay, so how are the layers to freeze decided? Okay, okay, so as it says here, okay, the basic idea is that we want to figure out whether primitive features that come in the basic bottom of the network, closer to the bottom, like say here, whether those features are stable, okay, and that we think we could use them for an upper level task, okay? Like I said, in doing something like computer vision, it's usually pretty normal to assume that things like light and dark, edges and corners, those are pretty important things, right? And that many types of tasks that we would need to have some idea of those things in order for them to compute higher level features, okay? So for example, using that to detect different types of man-made objects, um, tables and chairs, lights and chandeliers, okay, they all have edges and tables, okay? Now you can think, well, isn't that always the case? Are we always going to use things like edges and corners? Well, it really depends. If your raster image, okay, meaning your input image is mostly like white noise, okay? There's a whole bunch of noise in the picture, and then you're trying to classify one type of noise from another type of noise, then you can understand edges and corners aren't going to help you there because most of the images look like fine grains of sand. Okay, so it really depends on the task. So when we think that there's a lot of the task that is conserved against another task, then we will generally keep the other detections, okay, that we have. Okay, so as it says on this slide, this is the basic two pieces of information that you need to do to decide whether you want to transfer or not, okay? When there is not enough data, okay, let's say you have a very small data set, then you can do what it says in this image, right? Basically, take the whole network that's already been trained for another task which has sufficient data, okay? Rip off the top, we take that the penultimate or ultimate layers, okay? Rip off the top here, okay? And then replace it with a completely new head, okay? Which is uninitialized or randomly initialized, okay? And we're gonna say, well, basically what this corresponds to is that up to this point, I have pretty good high level image features, right? So if it's in the natural image space, I have, certain types of textures, um, landscapes, maybe, wood bark, fur, eyes, nose, ears, those types of features that we would see in everyday images, craggy rock faces, etc. So these are all different types of engineered features that came out of the previous task or the task that we trained on, okay? And then what I'm saying is those features are actually pretty useful when I'm doing a new task where the data is somewhat similar, okay? Okay, we always try to pick the task that we pre-trained from as close as possible to the task that we want to do, okay? So for example, if we're trying to detect consumer electronics, okay, and categorize those things, maybe we don't want to use something like ImageNet, which has mostly natural images or photographs, okay? We might use a data set that's comprised of other types of man-made objects like machines, gears, and parts, because we think the primitive features that would be used to recognize those things would be more meaningful for recognizing consumer electronics, for example. Okay, when we have sufficient data, okay, when we have a lot of data, what we might decide to do is, again, take the entire network as it is, okay, but retrain it. Just get rid of, instead of freezing it, okay, meaning that we leave the detectors as it is, we initialize the entire network with the previous pre-trained network's weights, but we let them vary. Okay, we say, for example, again, if I'm trying to do consumer electronics, but I only have ImageNet features, I'll say, well, these features might be a little bit helpful, but I need to tweak them. You know, I need a feature for glass or something. And in the natural space, there's no detector for glass. So maybe what the network can do is learn the concept of glass or something analogous to it through the use of changing the original features that I might have had here, 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 or here. Okay, so anywhere in the network. Okay, so I hope that helps you to understand when you do it. Okay, basically it all has to do with this keyword. Okay, data. Okay, if you have enough data, you can usually do better by doing it all over again. If you don't have enough data, then you need help, right? Just like if you're studying for a subject, okay, you might want to say, I want to trust a friend who has some experience in this area to help guide me along. So I'm going to transfer her knowledge over to me. And then she's going to teach me how to do this subject first, and then I will just fine tune what I know, right, by asking her questions. You know, oh, I got this concept, but I need to explain it back to you to make sure I got it. Okay, so when we do that, we're retuning our own understanding of what's going on. Okay. All right. Other questions that you guys have? Okay, so please go ahead. Remember that the Ask Me Anything is there. You just need to come here and then put it in, okay? And then we can discuss it. Okay, I will answer this question in a little while. Okay, so I will come back to that after the pre-lecture part, just to make that clear. Okay, well, actually, this is related to what we were talking about earlier. Okay, well, in both RNN and CNN for this particular problem, okay, so when we are thinking about locally structured, usually we mean something like in spatially, which would be CNN, okay, and temporally in the case of RNN, okay. Both of these means that when we look at how the features are being created, okay, we can find some group of neurons that are doing something interesting and preserving that information for downstream or sorry, for upstream use, right, for higher level feature analysis, okay. So when we see CNNs, okay, which we'll go through very soon, okay, we might find a circle as an important feature. Like we could use the circle detector for eyes, irises, wheels, balls, moons, or suns, right? So all of those things are spherical, right? They happen to be in different resolutions, okay? They could appear in different parts of the image, okay? So we want this particular detector to be able to be used anywhere it is, right? It doesn't matter whether the circle is in the bottom left or the top right, whether it's big or small, it's just simply a circle, okay? So by having a set of neurons that are devoted to understanding what a circle is, okay, then we can have enough data to learn that concept. Imagine if you have a circle detector in the bottom right, another circle detector in the bottom left, okay, they can only benefit from seeing circles in those particular locations, okay? And you already know that when you have little data for a particular concept, it's not easy to learn, right? So you get a lot of examples of the same thing. Oh, then I can master it, right? So that's the whole idea of saying that there's local structure spatially, okay? That we might find the circle detector, but at different resolutions or in different areas, it should be the same set of weights that are responsible for detecting that particular object or particular texture, some primitive feature, okay? All right. We're doing with our Ask Me Anything. Okay, so we have some questions, so let's take a look at those. Okay, give me a second here. Yeah, I need to stop presenting. Okay, then go back, so it'll take up the whole space. Okay. All right, so we finished this one, okay. And for unsupervised learning features, what we meant by input space, I think I covered that. That's the idea that things are either spatially coherent in a CNN or temporally coherent in RNN. The idea is we don't want to use a dense network with all of the edges. We only want to use some of the possible edges in a neural network so that we can represent things well, okay? Okay, so I just talked about pre-training as well. Okay, so I hope you understand what that meant. Okay, the idea is that when you have unsupervised learning to learn a representation of your input, okay, in the idea that I just showed you with autoencoders, okay, then maybe we have useful features that have been engineered to represent the data, okay, and using those representations is better than using a completely randomized set of weights for a node, okay? Won't ReLU cause the gradient to be 0 if it is negative? Yes, that's exactly the point. The idea is that we don't want to have a loss function that looks like this, okay? We don't want something that looks like this because that would just be a linear signal. What instead we want is something that's nonlinear. And the way that people thought about it at the beginning is that, a function that looks a little bit like this would basically kill off a neuron from doing anything, okay, if it was negative, okay, and then propagate the signal if it was positive, okay? So you can think about this in terms of what we saw on the lecture slides. So I'm just gonna go back here for a second, okay? This is post, okay, well, let me go back to the pre. Okay, so let's take a look at this network again. Okay, so if I'm using a ReLU, okay, and let's pretend I'm looking at this node over here, okay, and let's say the inputs to these nodes are all positive, okay, then it's going to output that information to its upper nodes, okay, so this information is propagating. Now let's say, for example, this other node here is getting inputs from our positive node, but also from these two, but somehow the inputs are not big enough to be positive, okay? Then this is going to get a 0, okay? So the 0 is going to basically make it ineffective for propagating any information, okay? So I won't be able to propagate anything forward. So this network, this input basically is destroyed, okay? If it's negative, okay? That basically means that this edge, and this edge, the ones coming out of this one, are turned off. They don't work anymore, okay? So there's another problem that we haven't covered, which is that ReLUs, when they're used in a large context and stacked over many things, it can actually make your entire network non-functional, right? Because if you have a whole bunch of other things turned off, okay, and we saw dropout, we also turn off things, right, with a random percentage, it's possible that in an entire layer, nothing is working. You turned off everything, okay? Then of course there's nothing to propagate and it won't work at all, okay? So there are some things that we do need to fix and people have fixed it, but they're not part of our introductory course, okay? Okay, so that was a lot of graffiti. But basically, yes, it does cause nodes to become useless as they won't ever update. So one of the problem with ReLU is dying nodes, nodes that are rendered useless after a while because they always run into this problem where their signal is negative and they cannot pass anything back. So they stop training, okay? What should the first set of inputs in an RNN be, okay? So let's take a look at that. So let's go a little bit down. Okay, so I think we're talking about this set. Okay, so in our first set, right, over here, we don't actually have any inputs coming in, right? So we have empty node and empty weight coming in. Okay, so we might randomly initialize them or set them all to 0. Usually, as we said in the neural network, we don't want to set anything to 0. We want to set it randomly perturbed, like a normal distribution. Okay, some positive, some negative, but not too large a value. Okay, so we'll use those as first inputs into the first time step. Okay, after that, we get the output at this part, at the activation, after we applied the nonlinearity, and it gets fed into the next node, right, at the next level. Okay, so that's a good question. Okay, so I hope that answers your question. If not, please ask again. I think it's important, right? How would data augmentation for structured or tabular data work? Is it useful as compared to image data augmentation? Data augmentation generally is important when you don't have enough data for your problem. Either you do that or you try to shrink your network so that you have enough information to determine a good weights. Okay, so that's a very important part. So if you want to use data augmentation for structured data, then you have to create new structured data in a perhaps supervised or unsupervised manner and provide it to the network. I'm not exactly sure what you mean by tabular data here. So if you can specify this question a little bit more, either in chat or here on the Ask Me Anything, I can try to address that. Okay. Okay. How do we know what the weights for kernels should be set in the conv layer? Okay. The important thing is we don't. Okay. We let the neural network learn. Okay. You remember in the lecture where we were talking about non-linear mapping, right? And we saw how if we had something like, positive things here and negative things here, we want to take our x1 and our x2 and then move them into x1 squared and x2 squared, right? And then we could get a classifier that can draw circles, right? So this was the idea where we're engineering these things by design. Okay, we have to come up with the method for doing it ourselves. Okay, the whole thing about a neural network is we are doing this nonlinear mapping by learning. Okay, we're actually not telling it what exactly are the kernel weights. We just start from a set of initial weights, okay, and we let the neural network learn by tuning what the weights could be useful to finding good nonlinear features, primitive features that could help with the classification task that we have downstream. Okay, so over time, after seeing many images, it will start to remember that, okay, I can see that, if I'm looking for a dog, there must be fur, okay, and there must be a set of eyes or something like that, okay, and then the layer previous will say, in order for me to know that there's eyes here because I'm an image map and I just happen to be activated when I see eyes, okay, it's just a function of the math. Okay, it needs me to see, dark things in the middle and light things on the outside that might have fur on the outside or something like that. Okay, so it is doing all of this by the virtue of learning, by using the loss function and trying to backpropagate this and trying to figure out, does this set of weights help me identify dogs and cats better or does it not? Okay, so this is the magic. This is the magic of deep learning, okay, is because previously, when we were doing learning and we have to create our own features, we have to do it by hand. We have to say, okay, symmetry might be a good feature for numbers, okay? So I'm gonna take the first half and the second half, fold them all together, take a difference, and that's going to be a feature. I had to engineer that from scratch. Okay, with neural networks, what I'm saying is that we're going to learn this. We're going to learn it in a process manner by saying, there are certain simple features that are composed into slightly more complex features, which are composed into slightly more complex features, again, until we get to the top of the network, which is saying I have these composite features that all help me decide whether there's a dog or a cat there, okay? Something like that. Okay, on question 5, I need you to actually identify which question you're talking. The 7-mark question, I think, is a, what is it? Candidate elimination algorithm. You can write your question into the forum, then we will take it there. It's probably better to do it worked out on the forum rather than through our lecture chat now. Okay, so we will get to that, but probably it's better to do it on the forum. So I'm apologizing ahead of time that I don't want to use our lecture time to do that right now. Okay, so I think we covered all of the Ask Me Anything for right now, except for this one, which I sort of didn't do for right now. But again, we will do that on the forum later on. Okay.